We're going to have another talk about glass, which is Khodor Sleiman. He's a researcher at the Laserzentrum Hannover, and I was happy to meet him digital. We actually never met in person, because he's part, or he's supporting our activity in 3D printing glass. There's within the 3D printing group, which Philip Rosendahl leads, there's a unit which does glass printing that's linked to Matthias Seel, who leads the glass group in our institute. And Khodor is the one really doing the printing on a very large, very small scale level in the beginning, but we are pushing them to come to certain sizes. And I'm happy to see how this comes from your background and actually really nicely wraps the whole package for today. So floor is yours. On you go.
Okay, thank you very much for the introduction. Yes, my name is Khodor Sleiman, and today I will talk about or present the laser-based additive manufacturing of fused silica components for structural glass constructions. About my talk, what the content of my talk. Yes, I will start with a little motivation, then go over to the state of the art, what kind of processes are already there to additive manufacture glass. Then I will go over to our experimental setup, and then to our applications in printing with a lower degree of fusion and a higher degree of fusion. And I will soon explain what this actually means. And then I will go over or conclude my talk with an outlook and in conclusion. So first of all, a little bit some words about the Laserzentrum Hannover. The Laserzentrum Hannover is located at the Wissenschaftspark Marienwerder in Hannover, Germany. It was founded in June 1986 and is an independent and non-profit research institute for photonics and laser technology. It is funded by the Lower Saxony Ministry for Economics, Labor, Transport and Digitalization. And it's focused on the research of optical components and systems, optical production technologies, and biomedical photonics. Inside the asset age, there are a lot of departments, and my group that I am located at is the glass group. So we deal with all kinds of laser-based glass processing techniques, such as 3D printing, coating and surface processing, marking, cutting, drilling, and also the welding of glasses. So without further ado, let's go right into the 3D printing part. Why is glass 3D printing even something interesting? If we look at the conventional glass processing techniques, which are still quite common in the glass processing, there are a lot of manual processes which have a high rejection rate and limited flexibility in the forming, which is not the case for the 3D printing of glass, where we join a high degree of automation and a high degree of flexibility. This is interesting for a wide range of applications, for example, optic systems designs, because new optical functionalities could be manufactured, and also in chemical and medical industries. There are a lot of complex glass components needed, for example, undercuts for channels and stuff like this. And this could be brought up with this glass 3D printing in the form of lab-on-chip applications. I think this is quite common. And in the architecture and civil engineering, it can be used for structural constructions where adhesive joints can be substituted. So it's better for the environment, it's able to be recycled better, and it's transparent, it looks better, and it's more durable. So there are already a lot of processes that can additively manufacture glass, such as fused deposition modeling technique, where glass is molded in an oven and deposited through a nozzle and deposited on a glass substrate, or the selective laser sintering process that is quite like the LPBF of metals, comparable. and the stereolithography process of glasomer, where they use a polymer matrix to embed the glass in it, and then the plastic will be sintered out. So they can form very small and precise glass structures. And last but not least, there's the laser glass deposition process, where a glass filament in form of a rod or a fiber is used to form complex structures. And this is the process that I use for my printing investigations. So we use a CO2 laser as a heat source, which is guided onto the surface of a glass substrate. And there the substrate gets heat up, and the fiber or a glass rod is fed laterally onto the surface of this glass substrate. So if we use a fused silica substrate, we also use a fused silica filament. And also if we use a borosilicate substrate, we use a borosilicate filament too. So the fiber gets deposited onto the surface of the substrate, and through a 4-axis system, we can deposit the fiber continuously and in complex shapes, because through the rotational axis, we gain direction independence. Yeah, and the temperature in the process zone is measured through a pyrometer, so we can precisely control the contact angle and the degree of fusion of the glass fiber. What does it exactly mean? So this means that the deposition morphology can be controlled precisely, and this leads or gives us the opportunity to manufacture in a wide difference of applications. For example, a high degree of fusion is more or better to build up microscopically components, because it's easier to stack these layers up. For example, for structural constructions, and also for multi-layer optic applications, for example, spherical lenses or stuff like this. A low degree of fusion is also very interesting, because there this form of the glass filament is still in the cross-section visible, and it's better for microscopically components. For example, single layer applications like optical components, which I can show you here. Yeah, so we could print spherical micro lenses like this, where the glass filament is just like heated up and then deposited at once onto the substrate. This can be used to guide light in optical networks, and also the printing of waveguides, where the light can be guided through this deposited fiber, and fiber tapes, and all kinds of other optical components. This can be used for telecommunication, sensing, optical networks, or yeah, you call it. So, but I want to go more near to the printing with a higher degree of fusion, where we use a disproportional deposition of the glass filament. So we use a higher feed rate than the axis speed to deposit the fibers. We conducted experiments to select suitable printed parameters for stability, transparency, and degree of fusion or contact angle. Because if you do not choose your parameters right, it might look like this, a shaky form, or it will have a lot of bubbles in there. Yeah, with these parameters, we try to investigate the possibilities of this process. What can we print with that? Can we print all the different yeah, 3D printing disciplines? For example, like a very standard ellipse contour shape, where we deposited the fiber continuously and rotated the substrate. And then we investigated it with CT to see how's the transparency or how many cavities are in there. So this is a picture of a CT scan, and this is like the only cavity I could find in the whole structure. We also see that the density is quite homogeneous and it is quite transparent. With the confocal microscope, we analyzed the surface roughness, which was around 1 micrometer. I think which is quite good for construction applications. Yeah, also we investigated the printing of overhang structures. You can see this here in the video and on the bottom, where we deposited the fibers with an overhang of 10 to 20% of the original track width. So we shrink the inner diameter continuously to form these conical structures. And then we did it the opposite to increase the inner diameter again. This process is quite stable for over 300 layers, what you can see here. The printing here, printing time was about 90 minutes, and it was still stable. You can also see the transparency of the structures. And these conical structures could be used for the application in architecture for point glass connectors. What we actually have shown on the Formnext at the beam stall. Yeah, with the cooperation with TU Darmstadt, like Professor Knag already mentioned. The TU Darmstadt conducted for us CT scans of the this conical point glass connector, and conducted also simulations for solidity estimations, and then we could laminate those point glass connectors onto on a glass window to show that these printed glass structures can actually hold a real load. Yeah. So a whole other discipline of 3D printing is the printing of free-form structures, which we also investigated. And we were able to print like these flexible glass springs or a glass bar into the air. In the bottom right, you can see the process, how it looks like in real time. So, and this opens up the opportunity to manufacture new mechanical glass components. So on the other spectrum of disciplines for 3D printing are the volumetric structures, which we also investigated in the form that we printed or deposited the fibers in a meandering manner next to each other with track distances between 0.5 and 1.5 millimeters. And we investigated the average waviness of the surface to see what kind of track distances are used to form a homogeneous surface. And we found out that a track distance of 80% of the original track width is quite suitable to form a low waviness of the surface. So on the top view of one layer, you can see that it's quite transparent, but for multiple layers, there are gaining the count of bubbles. In a cross section, you can see if we use actual optical fibers that have a refractive index change in the cross section, you can still see the interfaces, which can be used for optical applications, two-dimensional diffractive optics, for example. But if we use a standard glass fiber that has no refractive index change, you would not see these interfaces like you have seen at the beginning, like this ellipse-shaped structure. So for now, I will conclude my talk. So I've shown you the possibilities of the glass 3D printing for fused silica. So the question could arise: why did I use fused silica to show this? Because for the first steps to investigate the really possibilities of this process technique, it is easier to use a glass that would not break so much easy, like for example soda glasses. But for sure, the journey is going in this direction. For example, here you can see our first printing results with borosilicate glass. So we used a borosilicate substrate and filament and printed like this SLH. And here's the first prototype of a borosilicate lens. Yeah, and we will investigate more applications in every kind of or industry field. I thank you for your attention. These are my contact dates. And thank you again. I'm happy to hear your questions and happy for discussion. Thank you again.
Khodor, thanks for this view into this very detailed glass printing processes. And I understood from previous talks and the investigation which we do in Darmstadt as well that the main difficulty with printing glass is you want to get it on top of glass. So you either print the component by itself, but then it's just the object, or you need to print on top. And printing on top, that means you need to heat up the lower part to the same temperature, which then becomes a very interesting aspect. And yeah, the small components you showed, which were shown on the trade show on the Formnext stand, they were actually the smallest one which we had. It's a size of what, 2 by 2, but important for glass surface quality was very good. Any say fracture in the surface in glass would directly mean that's yeah, getting complicated. And I was impressed. I haven't seen that one. A glass spring. Well, that's super cool. For sure, we can identify new fields with that one. Or printing glass into the air. Another nice aspect.